Thank you very much for the introduction, and thank you very much for allow us to participate in the Digital Protection Using Group meeting 2022. Today we are presenting a work, and this work is basically based in a conference paper, a paper that was published in the DPSP 2022. And the title of this presentation today is Protection of a Six-Phase Transmission Feeder, Challenges and Solution of Modeling and Simulation. And the authors of this paper and this presentation over here, as you can see, Shen, Dr. Shen, Professor Peter Crossley, Professor Shandong Wang, and Dr. Xiaolin Din. And of course, I will be presenting this to all of you today. And well, it's very important to introduce here the agenda, and basically we are starting with a short introduction about the six-phase system. I will go extremely fast in order to identify the advantages of using the six-phase system. Then we will discuss the methodology about the implementation of the single pole tripping phase segregated current differential relay protection in DIOGSIELNT PowerFactory. Then I will present some simulation results using the software to show you the effectivity of the single pole tripping. And finally, we will have some conclusions. But let's start with a short introduction and telling you that we have been using three-phase AC three-phase system for many years. And the reason is basically an economic reason. However, the three-phase system has some limitations. Any one of you must know and must remember this basic equation over here that define the power transfer that can be used for lossless transmission lines. What I'm telling you is that the power flow here moving through these reactants over here depend of the magnitude of the voltage in both ends, and the reactance between the two terminals, and as of course the sign of the angle between those voltages. And if you plot this very interesting equation, you must remember that there is a maximum capacity that you can transfer. That capacity is defined by the maximum magnitude of the voltage at two terminals and inversely proportionally to the reactance. Okay. However, as you can see over here, the power transmission using three-phase system, they have some limitations, and that is related with the capacity. And now, if we go for a practical case, you can see here three different conditions for the GB system. The GB system has been experiencing a very accelerated integration of renewables. And in the previous years, the target for introducing more renewable has been increased. It's expected that for 2030, we will have more than 40 gigawatts installed. And those, of course, those variable primary energy resources, the offshore wind power, have the possibility of dramatically affecting the load flow, not only on magnitude, but also on directions. As you can see, the power flows in the electrical power system, in the GB system, is highly dependent of the wind. We have here three different scenarios: high wind on the right, low wind on the left. What is interesting for you is that during moderate and to high wind, the traditional load flow coming from the north to the south is still in the same way. What is interesting is that in the UK, we have a lot of generation, renewable generation at the north, and the main consume or the main demand is located at the south. However, the most challenging condition is coming from the low wind, that the power flows will start to be very chaotic. What I'm trying to tell you is that even for all the future scenarios, it's very interesting that the integration of this intermittent or this very variable resource of wind power will cause that the north-south power flow start to be highly variable, and is expecting that this north-to-south power flow will be constrained because the maximum capacity of the transmission lines. As I say before, in the UK there are some 400 kV transmission lines, especially double circuit transmission line, that they are moving the power flow from the north to the south. And what is interesting for us is that the large amount of the new generation that is basically coming from renewables in Scotland and the north can cause overloading in the northern transmissions and the northern transmission system. So as a consequence, we need to take two possible options. Or we reinforce the existing transmission lines, or we create more transmission lines, or we need to think out the box and try to find new solutions in order to enhance the power transfer capability from the north and the south. As I said before, the challenges on the power transfer capability on the existing transmission boundaries is one of the challenges for the GB system. And upgrading the system corridor, it's something that looks very logic, however, can face several practical problems. I will not go in details in those problems, but one of the possible clever ways to solve this problem is use what we call the six-phase transmission system. The six-phase transmission system is something that is not new, has been for many years, and probably the first publication talking about the use in the commercial side started in 1972. If we go to this secret report that is presented over here entitled High Phase Order Power Transmission, well, you can get more information about the comparison in numbers between the three-phase system and the six-phase system. And what is very important for us is that already in the United States of America in 1992, several research institutions and the government and the local transmission system operator in New York, they try this, they test and demonstrate the feasibility of using of six-phase system. But let's see how a six-phase system works. Well, many of you are familiar with the three-phase system. In a three-phase system, basically what we have is three phasors rotating at constant speed, that is the synchronous speed, and from there we generate or we produce in time domain three sine waves that represent the voltages. In a six-phase system is something similar. Now what we have is a large number of windings, and those number of windings are creating six voltages, and they are rotating at synchronous speed. However, we must be honest. In this presentation over here, we are not using the six-phase system coming from the generators. What we are doing is basically taking a possibility that is coming from transformers to create the six-phase system. And I will discuss a bit in a moment. Here you can see the phasor diagram between the three-phase system and the six-phase system. And there is a classical, a very important difference. In the three-phase system is 360 degrees divided by three phases, we get 120 degrees. But what is more important for the six-phase system is that the line to neutral voltage, they are separated 60 degrees. And that 60 degree create a very interesting geometrical property that we will discuss in a minute, okay? To show you the implementation, the real implementation of the six-phase system, what we will do is basically talk about the implementation, the demonstration that was sponsored by the Electrical Power Research Institute, EPRI, the Department of Energy in the United States, and several companies, local companies in New York. As you can see over there, there is an implementation of a six-phase system. And implementing six-phase system at transmission level is extremely simple. What we need to do is basically use transformers, and those transformers, they create the 60-degree phase angle. As you can see here, we have the transformer T1, and here we have the transformer T2. The transformer T1 is creating this three-phase system. You can see here the phase angle 120 between them. But if you look over here, there is another three-phase system rotated 60 degrees and is coming from the transformer T2. Again, we have here 120 degrees, but when we combine the two three-phase systems, voila, we have the six-phase system. Of course, we can create some more interesting configurations at the transmission system, but the possibility is also using a classical transmission line that have a classical double circuit. What I'm telling you is that for this practicality here for the GB system, what we are considering is a classical double circuit three-phase tower. And in this three-phase tower, what we are creating is two three-phase system. As you can see over there, they are three-phase system 1, three-phase system 2, but if we compare the phase angle between them, they are 60 degrees. And when we combine those three-phase system, voila, we have the six-phase system. Here there is a simulation using the 𝐃𝐈𝐆𝐈𝐓𝐀𝐋 PowerFactory, and you can see the 6 phasors where the phase angle between them is clearly 60 degrees. And the most important part to show you the importance and the use of the 6-phase system is coming here and tell you about the power. There are several differences between the 3-phase and the 6-phase system. However, the most interesting thing is related with the active power transfer. In a 3-phase system, we have line-to-line and line-to-neutral voltage, and the relation between them in the magnitudes is square root 3. However, in a 6-phase system, we have a 60-degree angle here. And to be honest, that creates a very interesting property, because here in the 6-phase system, we have 60 degree here, 60 degree here, 60 degree there. As a consequence, in this triangle, you can see that the line to neutral voltage is identical in magnitude to the line to line voltage. And when we use those properties here inside the active power definition, what we get is quite interesting, because we can see that the active power transfer in a 6-phase system is square root 3 times the power transferred by the 3-phase system. As conclusion, we can see that there is a 73% advantage of using the 6-phase system. By upgrading a 3-phase system to 6-phase system, we have the possibility of increasing the power transfer, and that is what we want to do instead of upgrading or creating more transmission lines. Here I will start to talk about the study case. In this study case, what we are doing is presenting a condition that we simulate inside the software. And here what we are showing you is that we have a boundary in a system. And you can see in this boundary over here, there are several transmission lines involved. In particular, here in the red color, we are interested on those two important transmission lines, UV1 and UV2. And the idea is that UV1 and UV2, they have a lower ampacity limit, and we want to increase that using a 6-phase system. And to do so, what we are doing is using transformers, and those transformers are star 6. And in this case, the original 3-phase system was 400 volt kV, and the line to neutral 231. But when we use the 6-phase system, remember that now we have the 60 degree, and as a consequence, the line to line and the line to neutral voltage is equivalent to 400. In the real system, there are some quadratic boosters. However, for this simulation over here, we are not considering that in the model. And the first simulation over here is a classic analysis. We are running a basic analysis for load flow, calculating the power flow in normal conditions and also in contingency. In this case, the contingency is the sudden disconnection of the transmission line UW. That means these transmission lines over here. And what we are interested in is in the power transfer that can be reached in normal conditions or a normal condition using the 6-phase system. If we use the traditional 3-phase, we have around 3,500 MVA, but using the 6-phase system, we have 4,200. And similar situation is happening during the outage. Having the 6-phase system provide a larger power transfer. You can see over here 5,448. If we use the classic three-phase system, using the six-phase is increased to 5,800. Now, what I will do is a short introduction about the fault analysis for the six-phase system. The six-phase system starts to be more and more complicated than the three-phase system because we have a larger combination of faults. In this case, we have 120 possible short circuit combinations. 23 of them are unique faults. And to be honest, using symmetrical components start to be quite interesting. If we are in a three-phase system, we have positive, negative, and zero sequence. And that is because we are using a three-phase system. But when we are using a six-phase system, of course, we have more components. We have the first, the second, the third, the fourth, the fifth, and the sixth sequence components. And that is because the number of possible lines increase from 3 to 6. In this paper, we are taking advantages of the short circuit calculation available in PowerFactory and also using the dynamic models inside the software. As I said before, we want to represent the UV1 and UV2, and we are doing so inside the software. Inside the 𝐃𝐈𝐆𝐈𝐓𝐀𝐋 PowerFactory, we are using two sources, one weak source and one strong source that is connecting two transmission lines in parallel. And in this case, we are using the two different transformers over here. One of them is creating a transmission system that is a three-phase system. The other one is creating the second three-phase system, and the phase angle between the two three-phase systems is 60 degrees. As a consequence, we have the magic of the six-phase system. And what is interesting is that line to neutral and line to line voltages for this six-phase system are equal, and that was a geometrical property that we already defined. Now we are talking about the possible protection, and in this case we are interested to protecting this six-phase system using a current differential relay. In this case, we decide to use the classical LFCB, and in this case we have included some time delays for the circuit breaker, 20 milliseconds for the circuit breakers in the six-phase line, and 60 milliseconds for the transmission three-phase side. And as you must be aware, the LFCB was originally created by the company Alstom. It was introduced probably in 1993, 1994. It's basically a true differential protection for 2 or 3 terminals, and it's basically a digital microprocessor-based design. And in this original model is included inside the library of the 𝐃𝐈𝐆𝐈𝐓𝐀𝐋 PowerFactory. And as you can see over there, the interesting part is that if you look the original model, you will find that this relay is using a single trip, but this trip is a three-phase trip. We modified this model, including the single-phase tripping, and as a consequence, we need to include a logic for the single pole trip, but also modify the internal logic of the relay to enable the trip for phase A, B, and C. And that is what we have done. It's something extremely simple, to be honest. What we are doing is modifying the frame. From there, we are modifying also the element relay in order to include the new logic and to include the single pole trip. And here we are talking about the logic that is related to the modified relay, including new signals, and what is very, very relevant for you to enable the single phase tripping is modifying the type logic trip. And in this case, you can see that we have defined single phase trips, double and triple, and all of them are combined for the outputs depending of the fault condition. If you want to have access to this model, what you need to do is just request to us, and we will be extremely happy to share with you that kind of model. Here is the classical differential characteristic. In this case, we are using the single pole tripping, and in this case, we are using the fault that is BCAN. And as you can see, there is a clear differential characteristic that is shown in blue color in this segment. Now we are trying to show the effectivity of the single pole tripping, and in this case we are using the instantaneous circuit breaker operational status for a fault that is BCABN. And in this case we are presenting the classical time domain representation for the currents that they are presented over here, and also the status of the tripping. As you can see over here, at the moment that the fault happened, there is a small time delay, as we say before, 60 milliseconds or 30 milliseconds, depending on the 6-phase or 3-phase system. However, the relay is able to identify and trip effectively. Then we run a test, and in this case, we run the 23 significant faults. As you can see over here, you can see all the list, and you can see how the relay behave by tripping and isolating the fault. Finally, a final sensibility analysis is basically considering different fault resistance, 100 ohms, 300 ohm, and 750 ohms. And from there, what was clear is that it was not a problem for selecting the fault phase independently until the impedance reached 750 ohms. Finally, here we have some conclusions. What is important to tell you is that we demonstrate that we can transform a 3-phase double circuit feeder into a 6-phase feeder. The only thing that we need to change in that feeder is basically adding one 3-phase transformer that allow creating two independent 3-phase system with 60 degrees between them. However, this system requires a robust protection scheme that it must be sensible and stable, and of course depending on the type of faults. And considering the importance of this 6-phase transmission feeder, we need to consider the single pole tripping. And we have implemented this inside the 𝐃𝐈𝐆𝐈𝐓𝐀𝐋 PowerFactory, and we have demonstrated that for the 23 significant fault types, the relay was able to identify and trip correctly. As a consequence, we have demonstrated that the single pole tripping is possible for the 6-phase system, and we achieve the 100% trip accuracy for all fault types. And this is all for the presentation. It's 22 minutes and 30 seconds, and we are ready for question and answer. Thank you very much for attending to this presentation, and it's time for question and answer. Thank you.